both constant zeros, the x and the zeta, we obtain that the components of that velocity remain zero and the motion is purely along the y-axis, as we can see here. This represents a straight line motion in the y direction, unaffected by the magnetic field, since the velocity is parallel to it. Then I integrate each velocity component to find the position vector over time. And this confirms that the particle moves uniformly in a straight line in the negative y direction as expected when velocity is aligned with the magnetic field and no electric field is presented. And that's all for our fourth situation. Let's go for the fifth one. Okay, for our situation 5, we have a magnetic force on a current carrying loop due to a long straight wire. We have to determine the magnetic field from a straight wire. We have to compute the magnetic force on the loop, to summarize the net force, and to do a diagram. So here is what I did from situation 5. We have an infinite wire and we have the total magnetic force, that is this one. We have our diagram and this is the magnetic field by the infinite wire, and the DL is electric current playing in the loop. First, I identify the geometry and orientation of the currents. One circular current I1 creating a magnetic field and another current I2 running through a rectangular wire loop. For the horizontal segments FM1 and FM4, I noticed that the magnetic force partially cancelled, while the vertical ones, FM1 and FM3, contribute differently due to their orientation and limit of integrations. So after integrating over the appropriate bounds, I sum all the force vector to find the net force. And I compare the magnitudes of force from the upper and lower parts, and I observe that the force of the segment FM4 was greater than the FM2. And that's all for the 5th situation. We go to the 6th situation. So in the situation 6, we have an experimental scenario, velocity selector using electric and magnetic fields. We have to determine the value of V0 for constant velocity. We have an alternative scenario where a magnetic field cannot be adjusted. We have to do a diagram and a conceptual analysis. So here is our situation 6. First, I start with the Lorentz force equation, that is this one. I consider also the condition for zero net force. And assuming that the velocity is only in the x direction and the magnetic field B is along the z-axis, I compute the cross product. So for the part A, for the particle to move undeflected, the electric and magnetic forces must cancel exactly. And we get this. And for the part B, I include components Bx, Bz, and Bj. Then we recalculate the cross product B times B, and we set the total force to 0. And at the bottom, I illustrate the direction of electric force, the magnetic force, and I show that they are equal and opposite when the velocity condition is met. The key conclusion is that the Fa and Fb cancel out. This because the magnetic force and electric force are equal. So that's all for our situation 6. We can pass to the last situation, that is our situation 7. For our situation 7, we have this diagram of a square and a rectangle. We have to determine the magnetic force experienced by the segment AB, BC, CD, and AA, and calculate the total magnetic force exerted on the loop, and then we have to go to MATLAB to write a code. Here is how I do the situation 7. Here we have the total magnetic force. Here we have our 4 segments, and our first segment is equal to 0. This is because I observe the direction of the current element dA and is parallel to the magnetic field B, so the cross product is equal to 0. Then the BC flows in the A zeta direction and the magnetic field is AJ. I compute the cross product and I solve it. For the segment CD, I perform a cross product of a differential vector in AX direction with the field. And for the DA segment, the current flows diagonally in both in AX and in A zeta, so I solve it. Using the determinant, I found that this segment produces a force in both in AX and in A zeta directions, effectively balancing out the previous forces. And finally, I sum up all the segment forces to get the total force. So now we're gonna pass to the MATLAB code to prove this. So here we have our MATLAB code, we run it, and we get our 4 segments. And that's all for my argumentative exam. I really enjoy it. I am grateful with my professor for teaching me, and that's all. Thank you very much. Oh, sorry, I just realized I forgot to do the analysis question from situation 6, so I will do it. Okay, they ask us to explain why this setup function is a velocity selector. Okay, this is because these setup filters charge the particle based on their velocity. So if the particle moves or too slow or too fast, the electric and magnetic forces won't cancel out. This causing that the particle curve and miss the target path. If the particle is too slow, it is pushed in the direction of the electric field, typically along the A. And if it is too fast, it is pushed in the direction of the magnetic force, which is perpendicular to both to velocity and B. And they also ask to describe what happens if the velocity of the particle deviates from the ideal value. So the particle does not travel in a straight line, meaning it gets filtered out or misses the target. That's exactly why this setup works as a velocity selector. Only particles with the correct speed make it through. And that's all. Thank you.